Okay, hello class. I want to, during this video, go through the solutions to the worksheet that I sent out to you last week. And then I want to get into the idea of constructing confidence intervals based upon a little bit different distribution called a t-distribution, which is more realistic of the kinds of things that we would actually do if we were performing some statistics. So the first question here was to construct and interpret a 95% confidence interval for the mean weight of all labs. Right, and they give us that the weights of labs are known to be normally distributed. Right, so with a sample of size 12, we're going to be okay with this central limit theorem with our sample distribution being normal. All right, so construct and interpret a 95% confidence interval. So from last week, we saw that the confidence interval looked like x bar plus or minus z star times sigma divided by the square root of n. So all we have to do is plug in our values, and our x bar was 78. Our z star for 95% confidence was 1.96. Sigma was given as 8, and the sample size was 12. All right, and so we end up with this confidence interval being 78 plus or minus. And when we do the arithmetic on this, we're going to get the margin of error to be about 4.52. And our confidence interval then is going to run from about 73.48 up to about 82.52. Okay, and then the interpretation of that is we are 95% confident that the true mean weight for all Labradors is somewhere between 73.48 and 82.52 pounds. Okay, and then Part B says, based upon your answer to Part A, is 80 pounds a reasonable weight for all labs? Right now, I would say that the answer is yes, because 80 is in this interval, and this interval really represents all plausible values that the mean could be. All right, now we're not going to say necessarily that 80 pounds is the exact weight, but it's a reasonable amount because it's one of the numbers that is in the interval. Okay, and then for Part C, would a 99% confidence interval be narrower or wider than a 95% confidence interval? All right, so again, like we talked about last week, if we're going to increase the confidence level, think about the idea of we're going to be more confident in capturing something, we're going to use a bigger net. So the margin of error is going to end up being bigger on this one, the confidence interval will be wider. And in fact, the margin of error up here was 4.52. If we calculate the margin of error on this one, the margin of error is z star times sigma divided by the square root of n, and in this case, that z star for 99% confidence is going to be 2.58, and then times sigma, which was 8, divided by the square root of 12, and you're going to get the margin of error here is about 5.96. All right, so the margin of error is 5.96 compared to 4.52 up here. Again, that's wider, okay? But really I want you to get the idea that not just mathematically is it wider, but why would it be wider? Higher confidence, bigger net. Okay, for the next one, another statistician constructs a 95% confidence interval to be between these two numbers. All right, and we're going to make a couple of assumptions here again that the standard deviation is 8, and the question here is what's the sample mean, and then what is his sample size? All right, so if we think about this confidence interval is going to be constructed as x bar plus or minus some margin of error, in this case z star times sigma divided by the square root of n. So if you think about this interval, you're going to have 74.14 is going to be a number on a number line. You're going to end up with 79.86 is another point on a number line. And then if you think about the margin of error is really the distance from the center to these two endpoints, and this is really where x bar is. X bar is just going to be the middle of the interval. So what you could do is say x bar is just going to be the average of these two numbers, or halfway between them, and you're going to find that x bar ends up being equal to 77. Okay? All right, and then how big is the sample size? Well, if the sample mean is 77, the margin of error, let me abbreviate that with MOE, the margin of error is going to be the distance from x bar to this upper value or from x bar to the lower value. Going from x bar to the upper value, we're going to end up with 79.86 minus 77. That's going to give me, what, 2.86? Okay, and that 2.86 is going to have to be equal to, he's got a 95% confidence interval, so the z star is going to be 1.96. His standard deviation is still 8, and then we're going to divide that by the square root of n. Okay, so solving this equation then for n, we're going to end up with 2.86 is equal to 1.96 times 8 is going to give me 15.68 divided by the square root of n. Okay, taking this a little bit further, if I multiply both sides by the square root of n, we're going to get 2.86 square root of n is equal to 15.68. If I divide both sides by 2.86, we're going to get square root of n is equal to 15.68 divided by 2.86 is going to give me 5.48. And then if you square both sides, you're going to get n is about 5.48 squared, which is about 30. Okay, so his sample size is going to have to be about 30 in order for us to get a confidence interval of 95% that is going to go between those two numbers. Okay, and then the last couple questions here. Question 3 just has to do with being allowed to do these mechanics. So the time it takes a student to commute from school each day is right skewed, okay? Think about it, some kids live close to school, but there's a few kids that live far away from school. And the standard deviation is 20 minutes, okay? One student takes a simple random sample of 10 commute times and finds the mean to be 32.52 minutes. He constructs a 90% confidence interval to be these two numbers. What's wrong with his approach? All right, now I'll tell you that mathematically, this is exactly correct. Okay, that this is, if you take 32.5 plus or minus, we're doing a 90% confidence interval, so 1.645 times sigma 20 divided by the square root of 10, you are going to get exactly this interval. All right, the problem is this. N is fairly small. That's less than 30. Okay, and the distribution is right skewed. So we're not going to be able to do a confidence interval based upon our procedures in this case. Okay, that is going to be meaningful. We can calculate it, but it's not going to have any meaning. Okay, all right, we're not going to be able to make any interpretations from it because of that right skewness and the small sample size. Okay, and then the next question then says construct and interpret a 90% confidence interval based on a simple random sample. All right, so now we got 40 students, and it's still right skewed, but even though the distribution is right skewed, our sampling distribution will be approximately normal because our sample size is large enough. Okay, so to construct this confidence interval, we'll take 32.5 plus or minus. 90% confidence is 1.645 for a z-score. And then our standard deviation was 20. And we're going to divide that by the square root of 40. And this is going to give us 32.5 plus or minus. And let's see. That margin of error ends up being about 5.2. And so our interval is going to range from about 27.3 up to 35.7. Okay, and then the interpretation of this is, again, I'm 90% confident that the true or the population commute times average is somewhere between 27.3 minutes and 35.7 minutes. Okay, again, I'm 90% confident that the population mean, okay, the mean commute time for all students at this school is somewhere between 27.3 and 35.7 minutes. Okay, and then again, this is about the interpretation of this. Another student believes that the mean commute time is 39 minutes. Based on your answer to part B, is the student's belief reasonable? All right, and so if we think about where is 39 relative to this interval, 39 is about 3.3 minutes above the upper bound. So I would say that 39 is probably not a reasonable estimate, and probably I would even go as far as to say it's an overestimate. Okay, it's probably much higher than what the true population commute time is. Okay. All right, so that should get us through that first part with just getting the idea of what a confidence interval is and how to construct it based upon Z procedures. But then, like I told you in class the other day, we are going to run into some problems because we're not going to know what sigma really is, right? And so there's an attachment that came with the email today, and it has got two problems on here that I want to work through with you. And I'm going to start out looking at this problem and seeing what some of the issues are going to be, and then show you this other distribution called the t-distribution, and then show you how we can use that t-distribution to construct confidence intervals. All right, so hopefully this is going to be kind of a baby step from what we did before. It's just we've got to adjust when we don't know what sigma is, and it's really unrealistic to know what sigma is if we don't know what mu is. All right, so here's a problem. Suppose you're interested in the mean amount of gas people put into their vehicles when they get gas at the gas station. You collect a simple random sample of 6 customers' purchases and find the following. All right, so these are the amount of gallons that people put into their cars, and we want to know is what is the population mean, okay, based upon this sample of 6 cars. All right, so we're going to construct and interpret a 95% confidence interval for mu. All right, so if we did this, kind of blindly with what we did before, we'd say this is going to be x bar plus or minus, and then z star, and then sigma divided by the square root of n. Okay, and then we're going to run into an issue here because we don't know what sigma is. Okay, so what we're going to end up looking at is our best estimate. And our best estimate for sigma is how much spread there is in the population should be fairly close to how much spread there is in our sample. All right, so I'll tell you that when you calculate the mean, you're going to end up with the mean amount of gas that people put into their cars is 10.75. And the standard deviation for these 6 cars is 2.51. Right, and this is the sample standard deviation, not the population standard deviation. All right, and so it seems like a reasonable thing for us to do is just to take this S and stick it in here where sigma is, and then just construct the confidence interval based upon S instead of sigma. All right, so that seems like a very reasonable thing to do, and it is a reasonable thing to do, but I want to demonstrate a couple of issues that are going to come up if we just blindly do that. Okay, that we're going to end up having to use a little bit different distribution other than the Z distribution. All right, so I've got a demonstration here with some software, and this is based upon, I'm going to take just a sample, and these are going to be a sample of IQ scores. Okay, and let's say that IQ scores are normally distributed. They have a mean of 100 and a standard deviation of 15. All right, so if you look down here at the bottom, this command is a command that is going to generate 3 IQs based upon a population that has a mean of 100 and a standard deviation of 15. So this command down here just says, go out to this population of IQ scores that has a mean of 100 and standard deviation of 15 and give me 3 of them. All right, and so when I do that, I end up getting these 3 numbers. Okay, I got some kid that had a IQ of 110, another one of 113, and another one with 124. Okay, these kids are all fairly bright compared to the average of 100, and in fact, this guy's almost 1 standard deviation above the mean, and this guy's about almost 2 standard deviations above, well, about 1.5 standard deviations above the mean. All right, so what I want to look at is calculating a couple things. First thing is the mean. The mean is just the average of these 3 kids' IQs. It ends up being 116. And the standard deviation of these 3 is 7.1. All right, now that 7.1 is the standard deviation of these 3, but remember the population standard deviation was 15. So this is kind of an under approximation for that standard deviation. All right, and then the next thing I want to look at is calculating some z-scores and then calculating something that we're going to call a t-score. All right, so let me take you back to here, and I want to just make a couple notes. All right, so if we went out to this population of IQ scores, okay, the mean of these IQs is 100, and their standard deviation is known to be 15. All right, so what I'm going to do is go out and collect a sample of 3 IQs, and I'm going to calculate a z-score. All right, and remember that z-score is just going to be an average x bar minus the mean, and the mean was 100, and then I'm going to divide that by the standard deviation 15 divided by the square root of 3. All right, so when I calculate a z-score, it's going to be based upon the sample mean, okay? And so if I go back to that software and I see, all right, I got a z-score of 1.88. So if you take 116 minus 100 and divide that by 15 over the square root of 3, you're going to get 1.88. Okay, these 3 kids right here are going to have a z-score of 1.88. Their average IQ is 1.88 standard deviations above the mean for all samples of size 3. Okay, now what I want to compare that to is what happens if we, all right, and again this is x bar minus mu over sigma over the square root of n. This is how you calculate a z-score. All right, and what we're proposing is to still take x bar minus the mean, but now put s in here instead of sigma, okay, because we don't know what sigma is. And when we do that, we're going to call this a t-score instead of a z-score. All right, just has a different name because we are putting in another estimate here where we should be putting in a known value. But the problem is we don't know what that value is. All right, so we're going to calculate the t-statistic by taking x bar minus 100 and dividing it by s over the square root of 3 in this case. All right, so going back to the software, that's going to give me this t-statistic down here. All right, now notice that this t-statistic ends up being quite a bit bigger than this. Okay, this is 3.9. You can still think about this as standard deviations above the mean, all right, but it's based upon a sample standard deviation instead of population standard deviation. All right, so what I want to demonstrate next is if I went out and collected lots and lots of samples, right, and the way that I'm going to do that is I have this set up so that it's going to calculate a z-score and a t-score for different samples, and it's going to just capture those numbers here, and then it's going to produce 2 graphs over here. Okay, the one that I put up here on the top is going to be should end up looking like a z distribution, and the one down here is the t distribution. What I want to focus on is how are these 2 graphs similar and how are they different. Okay, and so on this software I can just tell it to go out and get another sample of size 3, right? And so there's a new sample. Okay, I got one kid's got a 78, 104, and a 99. Those 3 kids have an average of 93 or 94. That's going to give me a z-score of negative 0.7 and a t-score of negative 0.75. Right? And one reason that these 2 things are so close together is because this 13.97 is pretty close to 15. Right? So these 2 formulas are giving us almost exactly the same value. All right, and so it's going to record that number up here, the t statistic and the t statistic and the z statistic, and then it's going to produce these graphs over here. All right, and then I can just say do it again and again and again and again. All right, and so what we're going to end up doing is building up these sampling distributions based upon our formulas. All right, so if I keep doing this for a while, all right, this is just producing hundreds and hundreds of these samples and calculating t statistics and z statistics. And if I let this run for a while, we should start to see some similarities and some differences in these distributions. Okay, that should be enough for us to get kind of an idea what's going on. All right, so first of all, let's look at this z distribution. This z distribution is, first of all, mound-shaped. Okay, and not only is it mound-shaped, but we should expect to get values that range from -3 to +3. This is a z distribution, or at least very close to a z distribution. And if you look at what's going on down here, one of the similarities is that this is centered at 0. Okay, these are stacked up close to 0, which just means that we're going to get a lot of sample means that are around 100. All right, and then the other thing you should notice is that this is fairly normal looking. Okay, when I say normal looking, I'm saying it's mound shaped, but I'm going to say that the big striking difference here is that this distribution has a range of about -3 to +3. This one's got some of these numbers that are out here a little bit further. All right, and this one's got more variability than this one does. All right, and so if you think about this is a sampling distribution, but the difference is that this is a t distribution based upon samples of size 3, and we're comparing that to a z distribution. So if you wanted to compare these two, the z distribution is going to look something like this. And this is the z distribution. And the t distribution, when we're taking samples of size 3, is going to look more like this. It's going to be wider and more spread out. All right, so t distribution is going to look something like this. Has more variability. All right, it's still mound-shaped and looks kind of normal looking, but it has more variability than the z distribution does. Okay, now I want to go back to that software and see what happens if we were to take different sample sizes. All right, and so let's increase that sample size to, let's say, I don't know, 16. All right, so we can do that by going back to our document, and all I have to do is change this to 16. Okay. And so we're going to get 16 IQ scores here. We're still going to calculate the mean and the standard deviation, and we're going to calculate a z statistic and a t statistic. But now what I want to do is start generating these values again, and I got to get rid of the ones that are here first. I maybe shouldn't have done so many here. Oh well. All right, come on. Okay. All right, so now let's go back up here to the top and we'll play this game again. Okay, we're going to go out and collect samples of 16 IQ scores and calculate Z's and T's, and then what I want to look at over here is what's happening to this distribution. Okay, so here we go again. Another T, or another sample, another T, and another Z. Another one, another one, another one, and so on. All right, and if we keep going with this, all right, I want to look at how do these distributions compare. All right, and that should be enough to get us going on this one. All right, so again, we're seeing a z distribution show up here. It's a normal distribution with a mean of 0 and a standard deviation of 1. Okay, and it's got a range from about -3 to +3. This one is similar, but it's going to have a little bit bigger range. Okay, it's got more variability again. And so, but this looks different than the graph that was up here before. The one that was up here before, and we had some numbers out here around -8 and -6, and also some numbers out here. So this one's becoming less, I mean, it's more variable than this one is, but less variable than the first one was. Right, and so if we go back to our notes here, oops, I don't want to do that. Go back to our notes. Okay, there's really, this is based upon a sample of size 3, is this t distribution. But then if we take n equals 16, we're going to get a distribution that looks a little bit different than both of these. Okay, it's still going to be more variable than the z distribution, but less variable than this red t, and so we're going to end up with a graph that maybe looks something like this. Okay, and this is still a t distribution. Okay, but this is based upon a sample of 16 instead of a sample of 3. So let me just put 16 here, and we'll put sample size 3 here. All right, so one thing you should notice is that this t distribution is actually a family of curves. Okay, and the family of curves is going to all be kind of mound-shaped, centered at 0, but has less and less variability as the sample size increases. All right, and what we're going to do is we're going to describe this t distribution as a t distribution with a certain degree of freedom. And the degree of freedom is just the sample size minus 1. All right, now what we're going to end up doing with this t distribution is we're going to use it in a confidence interval. All right, and the way we're going to use it is this. So we have, let's say, a 95% confidence interval. For mu. Our structure is going to be x bar plus or minus, right? And then in here we had a z star. Well, we're not going to be able to put a z star in there because we're not going to be talking about a normal distribution anymore. We're going to be talking about a t distribution. And then we usually had sigma divided by square root of n. Now we're going to have s, the sample standard deviation, divided by the square root of n. All right, now instead of putting a z star in here, we're going to put in a t star. Okay? And what we're going to be looking at to put in a t star is we're going to be looking at the normal, or not the normal, but a t distribution with a certain number of degrees of freedom, n minus 1 degrees of freedom. And what we're looking for a 95% confidence interval is if this is t and this is negative t, we want 95% to be in between the two. All right, so the next thing we have to look at is how to use a table for this. All right, and I've given you a table that is probably very similar to the one that you have along with your z table from your book. And this is one that we're probably going to use this table more than we use the z table because there's not really a nice way to do an inverse t. All right, so here's the idea on this. We're looking for, let's see if I can do both of these in one picture. Let's see. Escape. Okay, so what we're looking for is the value of t that cuts off the middle 95%, all right, which means that this over here is the top 2.5%. Okay, so if we look at the table, first of all, this table is going to be read quite a bit differently than the z table is. First thing we're going to look at is we're going to go over here to the degree of freedom. The degree of freedom is in this column, and each degree of freedom is going to have a different graph, and it's going to have a tail probability that is given here. Right? And if you notice the picture up here, the probability is the right tail. All right, so let's say that I'm looking for, go back to our original problem with the gas mileage. If I can find it. Okay, so this was our original problem. All right, let me make that big again. Okay, so construct a 95% confidence interval for mu. All right, so our confidence interval is going to be x bar plus or minus t star s over the square root of n. So our x bar was 10.75 plus or minus, let's leave this blank for now, s was 2.51, All right, and I just get that from doing one variable statistics on my calculator, divided by the square root of 6. All right, and then what we need to do in here is put in our t star, and our sample size was 6, so we're going to find a t star with 5 degrees of freedom. All right, so to do that, let's go back to our table, and we're looking for 5 degrees of freedom, and we're looking for that t statistic, or that t value, that cuts off the middle 95% in between, which means that this upper tail is going to be 0.025. Okay, so to read this from the table, we go to 5 degrees of freedom, and we go to where we find 0.025 across the top. Okay, this is our right tail probability, and we look at the intersection of that column and this row, and we find 2.57. Okay, so the number that goes in here is going to be 2.57. Okay, so now my confidence interval is just 10.75 plus or minus 2.57 times 2.51 divided by the square root of 6, and we're going to end up with our confidence interval being 10.75 plus or minus, okay, this margin of error ends up being 2.63 when all is said and done, which is going to give me an interval that goes from 8.12 to 13.38. Okay, so nothing is really all that different on this. Nothing is all that different. It's just that what we're doing is we're using a t-distribution to come up with this because we're using S where we should have sigma. Okay, the interpretation of this is still exactly the same. Okay, I am 95% confident that the average amount of gas purchased at this gas station for all vehicles is somewhere between 8.12 gallons and 13.38 gallons. Okay, now it seems like we've done a lot of stuff here, but really all we've done is the fact that we don't know what sigma is. We put our best estimate in there, and if we estimate that, we're going to have to use a little bit different kind of a distribution here. Those are the only two things that are different. Otherwise, everything is exactly the same. Okay, so let's try another one. Suppose that we're interested in estimating the mean date that is stamped on all pennies in circulation. Okay, we did a problem kind of like this in class. All right, and what I want to do is suppose that we collect a simple random sample of 39 pennies and record the mean. Sample mean is 1993, and the standard deviation, this is the sample standard deviation, again, not the population standard deviation, and you notice that it's denoted with an S instead of a sigma. Okay, construct and interpret a 90% confidence interval for the mean. All right, so again, our confidence interval is going to be X bar plus or minus T star. We've got 39 pennies, so we're going to have 38 degrees of freedom, and we're going to have S over the square root of N. Okay, so then some of these things we can just plug in. This will be 1993 plus or minus. Okay, we need this T star. I'm going to leave that blank for now. We'll go back to the table. Our standard deviation is 12.3, and our sample size was 39. Okay, so we're going to go back to the table, and we want to find out what is the t statistic with 38 degrees of freedom. So this is the t statistic with 38 degrees of freedom, and we want 90% to be in between these two numbers, which means that in this right tail there's going to be 5%. Okay, so let's move this out of the way. Make this smaller. And we're looking for 90% confidence, so our right tail probability is going to be 5%. We go down to 38 degrees of freedom, and the problem is we don't have 38 degrees of freedom, but we do have 30 and 40. All right, and so what we're going to do is we're going to just round to the nearest integer that shows up here. And you should notice that in that column, this is the 5% column, go down to 30 and 40 degrees of freedom. You should notice that these two numbers aren't too far apart. Okay, because a t-distribution with 30 degrees of freedom and a t-distribution with 40 degrees of freedom are nearly the same graph. All right, so we're going to use this one, 1.684. 1.684. Okay, so now to construct our confidence interval, all we have to do is punch into our calculator 1993 plus or minus, and I didn't do this one ahead of time, so bear with me, 1.684 times 12.3 divided by the square root of 39, and that gives us 3.316. Okay, I'm going to call that 3.32. And so our interval is going to be 1993 minus 3.32, gives me a lower bound of 1989.7, we'll call it, and an upper value that's 1996.3. All right. So our confidence interval again is, the interpretation of this is, I am 90% confident that the true mean date stamped on all pennies in circulation is somewhere between 1989.7 and 1996.3. I'm 90% confident that the true mean is somewhere between those two numbers. Okay? All right, so you're going to end up using that table, and there's a couple of other things I want to show you on that table. You are free to print this one off and use it, or you can use the one that came with your book. The only reason I'm showing you this one is because I don't have that one that came with the book handy right now, but it should look very similar to this one. One of the things that you can do also is, we're looking for this upper tail probability is going to be basically half of what's left over. If we're doing a 90% confidence, then this is going to be 5%. If we're doing 95% confidence, this is 2.5%. So you can look at this right tail probability up here on the top, but what might be even more handy is to look down here at the bottom. Okay, so if you look at, there's 90% here, that corresponds to 5% in the upper tail. If there's 2.5% here, that corresponds to 95% down here, and so on. So you might be looking at these numbers a little bit more than you're looking at the numbers at the top of the table. Okay, so I think that should get you through the other stuff with confidence intervals using the t-distribution. And so going back to your syllabus, let's see if I can pull your syllabus up here. Let's see, find your syllabus here. And what I'd like you to do for homework for Thursday is to work through the rest of these problems with using the t-distribution, which is on your homework sheet is this part right here, page 349, okay, from section 7.3, and this is all using the t-distribution instead of using the z. Okay, and then also looking ahead, I'm going to move on to hypothesis testing next time. Okay, and hypothesis testing uses a lot of these same concepts, but the idea is we're trying to test whether or not some claim about a mean is true or not. And then we're going to end up kind of skipping over some of the stuff that's here. And then looking ahead, we've got this week we're doing estimating mu with an unknown sigma. We're going to do hypothesis testing. And then we're going to look at this idea for testing means, and we're going to eliminate this estimating the variance, and then also this variance and standard deviation tests. So I do want to talk about proportions, and I do want to talk about means. So we're going to kind of shore this up a little bit. We'll have an exam 3, looks like it'll be sometime next week. We'll have a day to review for the final, and then our final exam will be looks like June 11th. Okay, so I will get back to you again later on this week, and I'll take questions on these, and then I'd like you to keep working on section 7.3 for homework for Thursday. Okay, thanks. I'll see you later. Bye.